All right, this is lesson 613. Today we'll be working with comparison mats, and we'll be stating steps, justifying steps to make sure that they're legal. So our first problem, Maria is working on a set of comparison mats, and she has been called away. So Garth looked at her work, but he can't figure out what Maria did to get from one step to another. She didn't justify her steps. So what we need to do is we need to justify what is that step that Maria took. We're going to justify her moves. To justify means basically to give a reason. All right, so if you look at the first step, we have 5x plus 2 plus negative 6, 2x plus 2 plus negative 8 becomes 5x plus negative 4, and mat B becomes 2x plus negative 6. So what has happened in this case is the 2 and the negative 6 became a negative 4. Okay, so these terms were just basically combined because they are like terms. Okay, so our first step was the original expression, and then the 2 and the negative 6 became a negative 4, and the 2 and the negative 8 became a negative 6. Okay, so this is, we're combining our like terms. And if we were working with the tiles, this would be basically doing 0 pairs. Okay, 0 pairs means you have 2 positives and 8 negatives. 2 positives cancel out 2 negatives, giving you 6 negatives. So like terms is what's actually happening. And then step 3, 5x plus negative 4 becomes 3x plus negative 4. And then this becomes negative 6. What has happened is we're removing the 2x. 2x's leave this mat A, and 2x's leave mat B. So remove 2 x's. And then from step, the final step, how did 3x plus negative 4 become this? We removed the negative 4. Is that the same thing that happened here? Yes, 4 negatives go away, leaving you 2 negatives. So we are removing 4 negatives. Okay, subtracting 4 negatives, kind of be the same thing as adding 4 negatives, but in this case, we are taking them away. So when we look at our next comparison mat, we're going to build this comparison mat. So we have 2 plus 2x plus negative 3, and 2x plus negative 4 plus 1. So this is going to be mat A, and this is going to be mat B. So here's mat A on the left. We have 2 plus 2x. There's 2, and here are 2 x's. Remember, we're not drawing them. We're just putting the pluses for 1s and the minuses for negative 1s. And the same with x's. We'll put a negative in front of it. Okay, and then plus negative 3. So we are going to put 3 negatives there. And 2x plus negative 4 plus 1. There's 2 x's. There's negative 4. And here is a positive 1. Okay, so on the left, let's just copy this expression down. I'm going to call it minus 3. And on the right, we have 2x minus 4 plus 1. Okay, this is the original expression. Now, the first legal moves that we're going to do is, let's do our 0 pairs, just like we've been doing all along. So we have 2 positives and 2 negatives. That's positive 2 and negative 2. And then on the right side, we have a positive 1 and a negative 1. So those can go away because zeros don't affect, leaving us with 2x minus 1 on the left, and on the right, 2x minus 3. And if you look at the numbers, that is what's happening. 2 and the negative 3 becomes negative 1. The negative 4 and the 1 become a negative 3. Okay, so these, again, we're combining like terms. And our next legal move would be to remove matching parts, the identical tiles on both sides. So we can start with 2 x's that appear in both of these. So we can take away 2 x's, we can take away 2 x's, and that leaves us with a -1, and a -3. Okay, and we removed 2 x's. So at this point we could tell which one is bigger. Mat A is bigger than mat B by 2, so this one is greater than. Now even though we can do another legal move because we still have identical tiles in different parts, we have a -1 here and a -1 there, not completely necessary that we go that extra step, okay, because this gives us the same result. Mat A is bigger by 2. And as long as you do the legal moves, it's going to be the same relationship. All right, so we remove -1. Okay, now let's move to the next one. So in this one, we're going to use the expression and write what's on the left, what's on the right, and then what that step was. All right, so we're going to call them mat A and mat B. So mat A is going to be here, mat B will be there, and then we'll put the step. All right, so first we're starting off with, let's name this. This is called 2x plus 3 minus 1. 3 positives, 1 negative. This is x plus 5. Now, looking at our symbols and numbers, we can see, oh, we do have like terms. We don't have any like terms here. And then you can see the connection with the tiles looking at the opposites and the 0 pairs. All right, so we're going to try to make a transition from the tiles to just the symbols. So let's go ahead and take out our 0 pairs. We have a -1 and a +1, and then no more 0 pairs. So what that leaves us with, this was the original expression, 2x plus 2, there's that 3 and -1, and then x plus 5. That was unchanged. And what happened here was, let's just call it like terms. All right, and then our next legal move would be to remove what they share on both sides, the identical tiles. So we have 2 positives, 2 +1s on both sides, and that gives us 2x, and on the right it gives us x plus 3. And what we did was we subtracted 2. And let's just put the symbol now at this point. We're removing something, we're subtracting it. Okay, removing a negative would give us 2 negatives here. All right, next step. We are going to take away an x from both sides because we can. That is a legal move since we're keeping the balance. And that leaves us with x on the mat A and 3 on mat B. And we subtracted x. Right, so what is left is an x and a 3, so which one is greater? And we learned in a previous lesson that we can't tell because x could be any number in the world. So our task is, let's find 4 values for x that will make mat A greater. So when will mat A, which is x, be greater than 3? Okay, well that will happen if x is, well, x can be 4, x can be 5, or any number greater than that. Okay, so any number that follows that in a sequence. Okay, so these numbers here are called solutions. Okay, all these numbers, and 4, 5, and 6, since they're solutions, they would make this a true sentence. Okay, so any value for x that makes A greater than B is a solution for the original inequality. So let's answer this question here about the solutions. Now, is there a greatest number that is a solution? So a number where you say, you can't go any higher than that number, right? So we know 4, 5, 6, ... means that we can go on forever. You can take 1,000,000. 1,000,000 would be a solution because 1,000,000 is greater than 3. So is there a greatest number? No. the numbers can just be any number greater than 3. With pretty much no limit. And our next question is there a smallest number that's a solution? So that means, is there a smallest number where you say, okay, this number is greater than 3, but you can't go any smaller than that little number of which is greater than 3? Okay, and you might think, well, 4 would be the lowest whole number, right? But when you think about it, you have numbers such as 3.1. Okay, 3.1 is greater than 3. Can you go smaller than 3.1? Yeah, you can go 3.01. That's a smaller number that's greater than 3. Can you go smaller than 3.01? You can go 3.001. And so on. So you can keep getting smaller and smaller and smaller by adding zeros and zeros, and this can pretty much go on forever. So is there a smallest number that is a solution? And the answer is pretty much the same. It can be any number greater than, and let's put 3.0 because we're thinking of the smaller numbers and the decimals. Okay. Now that number that we're talking about is called the boundary point whenever we have an inequality. That's where the solutions end. Okay, so the boundary point is where the solutions end. All right, and we're going to highlight that part because boundary point is a very key part of this lesson. So the boundary point means, oh, it can't go any bigger than that, can't go any smaller than that. Okay, but we can keep going smaller at certain instances. So now, what we're going to do is we're going to graph it. What if x was greater than 3? How would we graph that? Okay, so here's what we are graphing. X is greater than 3. So our first step in graphing an inequality, let's put the steps here. Okay, so step 1. What we're going to do is mark the boundary point. So if x is greater than 3, where do all the solutions greater than end? Where do all the solutions less than end? They end at 3. So basically that number that's being compared to x. So we're going to put a circle on a little bit above the number line at 3. Okay? Put a circle on the boundary point. So there's the boundary point 3. Step 2. Now, if the boundary point is a solution, we are going to shade it in. So shade in the circle. If the boundary point, I'm going to call it BP. Okay, let's put BP here. Okay, so I'm going to shade in the circle if the boundary point is a solution to the inequality. Okay, so is 3 a solution to this? 3 is greater than 3. Not true. So we are not going to color in this circle. We're going to leave it unshaded. And then step 3, we're going to draw an arrow from the circle in the direction of other solutions. Okay, so let's look at other solutions that we can plug in for x is greater than 3. So we start to the left. 2. Is 2 greater than 3? No, it's not. So let's look to the right. Is 4 greater than 3? Yes, it is. So that means we are going to go to the right, because 4, 5, 6, and all those other numbers are solutions to x is greater than 3.